Hey Pre-Calc students, in this video we're going to cover limits algebraically. So the first thing that we're going to talk about is the order of kind of like how you should go about finding limits algebraically when approaching a value or a number. So this is like when x is approaching a value like 3. So step 1 is always going to be to plug that x value in to the function. If you get a y value, then this y value is your limit, and this means that the function is continuous. We'll look at an example of that. If you plug in and you get a y value of 0 over 0, then this is what's called the indeterminate form. Whenever you get 0 over 0, there's some algebra you can do to determine that limit. So we're going to use algebraic skills to simplify and then retry plug in. The algebra skill that we're going to focus on for this video is factoring. And the last option is if you get two different y values or a number over 0. The two different y values can only come from a piecewise function. And what happens is you're having to check two different sides of that to see if they're the same. So you'll have to check both a left limit and a right limit. Talking about really quickly a number over 0, because I actually don't have an example in this video about this. If you have a number over 0, this is coming from a rational function with a vertical asymptote. So for example, if I tried to approach 0 on 1 over x, I would get the number 1 over 0. This is true because at 0, the function 1 over x has a vertical asymptote, and we say that the limit does not exist here. In fact, for anything in this category, if you get two different y values or if you get a number over 0, you'll always use the expression does not exist. Okay, let's take a look at this first problem. Find the limit as x approaches -2 on the cubic function x cubed plus 6x squared minus 16. So our first step is to always try the plug-in method. So we're going to plug the -2 value into the function. We're going to simplify by following order of operations. So I'm going to evaluate all my squares, or all my exponents. I'm going to multiply, and I'm going to combine all my addition and subtraction. Okay, once I have this, when you get a y value, this is your limit. Also important to understand, for your limits algebraically, we're only normally ever talking about the double-sided limit. This is both the left and the right side. So this is the left and the right and the overall limit. Just to show you what this looks like on a graph. As I start on the left side of -2 and I approach from the left, I'm approaching the y value 0. And then as I start on the right side of -2 and I approach from the right, I'm approaching a y value of 0. So again, just to illustrate that on the graph, as I approach from the left side, the function's going down to 0. The right side, the function's going up to 0. Pause the video and try number 2 on your own. So here again, just to show you the graph of the last one, I got the limit of 3/2. So as I approach 2, again from both sides, the left and the right, the function's value is approaching 1.5, which is 3/2. For our next example, we're going to take a look at limits of piecewise functions. And piecewise functions are defined by pieces being broken up by the specific domains. So the f of x function that's being defined is x plus 1 is the function when x is less than 2, and the other function 2x plus 1 when x is greater than or equal to 2. So you have the function, you have the domain of the function, and it's kind of piecing these two linear functions together on the domain. When we're finding the limit as x approaches 2 on this function, because limits do have pieces, we do have to check both the left and the right side. So the first thing that I'll do is I'll talk about the left side limit. So I'm going to break this limit down, and I'll do the limit as x approaches 2 from the left-hand side on this f of x function. To describe the left-hand limit, I need to use the piece where I'm using values below 2. So when x is less than 2, this is the left piece, and this is the equation that I'm using for my plug-in. So I'm going to plug in to x plus 1, and again, I'm plugging in the value 2. When I plug that value 2 in, I'm getting a left side limit of 3. Now I'm going to do the same thing, but I'm going to do for the right side. To talk about the right side limit, I'm going to first break this down and write it in limit notation. And to find the appropriate piece, I want to use the greater than. For limits, it never matters when x is equal to the value, because again, we're only ever dealing with values really close to the number you were approaching, but never the exact number that you're approaching. Okay, so then I'm going to use the piece 2x plus 1, and I'm going to plug in the value 2. Again, the reason why I'm plugging in the value 2, even though I'm talking about numbers right above 2, I'm almost like rounding, so that I'm plugging in a number so close to 2.00000000001, and I'm kind of seeing, I'm approximating that value to see what it's approaching. Okay, and on the right side, I got a value of 5. I think it might be helpful to take a look and see this graph of this piecewise function, so I'll graph this in Desmos for you. Okay, so essentially a piecewise function takes a function and gives it a very specific domain. So I have the function x plus 1, but the x plus 1 function only lives when x is less than 2. And then 2x plus 1 is this linear function, but it only lives when x is greater than or equal to 2. So you can kind of see that the left side is going to the y value 3 and the right side is approaching the y value 5. And because the left and the right side are not the same, the question that we were originally asked was about the overall limit. And whenever the left and the right are not the same value, we say that the overall limit does not exist. So our final answer for our original limit as x approaches 2 is it does not exist. Pause the video and see if you can try this next one on your own. Okay, just to talk about this, I said that the limit of the function f of x as x approaches 2 from the left is the same as the limit as x approaches 2 from the left on this linear function x plus 1, plugged in 2 and got the value 3. I did the same thing for the right side when x is greater than 2 using that piece of that function, and also found a limit value of 3. Because the left limit and the right limit are the same, I can say the overall limit of the function f of x as x approaches 2 from both sides is the value 3. Really quickly, just to talk about what this middle expression is talking about, x squared when x equals 2, I'll show you the graph and that might help you understand what this is talking about. Okay, I have the first linear function graphed in red, the quadratic function that's actually only defined when x is 2 graphed in blue, and this second linear function graphed in purple. So the limit is talking about as I approach 2. So as x approaches 2 from the left, as x approaches 2 from the right, we're approaching this open undefined circle of 2, 3. And then this closed circle is just an extra point on the graph, but I do not approach that point as I get close to 2. Okay, the next thing that we'll talk about is when you... Okay, the next two examples are focusing on when there's an indeterminate form, meaning 0 over 0. So again, you should always try direct substitution first, and the indicator that you'll need to do more is when you get 0 over 0. So just to kind of quickly show you, number 5, we have the limit as x approaches -4 on the function f of x, and then f of x is being defined as this rational function x squared plus 3x minus 4 over x plus 4. Just quickly, I'm going to do the substitution work, so I'm going to plug in -4 into this function and show you what I get. Okay, I got a value of 0 over 0. This does not mean this is the answer to my limit. This just tells me that my form is indeterminate, and I can do some algebra to figure out this limit. So what I'm going to do is I'm actually going to, and we'll focus on the factoring technique. So there's an algebra skill that I can do to make this function f of x into a different form. So I'm going to factor this function. My factors in my numerator are x plus 4 and x minus 1, and the factor in my denominator, it can't be factored, so it's just x plus 4. And then I notice that I have a common factor in both the numerator and the denominator, so these can reduce to 1, which means my function f of x can be reduced to the linear function x minus 1 divided by 1, but I don't have to put 1 when it's in the denominator. So this is a reduced form of my function f of x. And because it's a reduced form of the function f of x, I can use my reduced form to find the limit. So now I can say that the limit of the function as x approaches -4 on the function f of x is equal to the limit as I approach -4 on the reduced function. Plug-in should work here. If I plug in -4 minus 1, I'll get the y value -5. So this is the value of my limit. Really quickly, worth showing you the graph of this function. Okay, so here's the graph of the original function that was x squared plus 3x minus 4 all over x plus 4. If I try to find the function's value, the output value at -4, you'll see that that value is actually undefined, which is why when I plugged in, I got 0 over 0. So what I did instead was graph the reduced form of the function. The reduced form of the function is the exact same as the original function, but now if I trace the reduced form of the function, that value is now defined. So when I plugged -4 in, I got out the y value that I was approaching, and the y value that I was approaching was -5. Okay, pause the video and try 6 on your own. Pause the video to check your work. I didn't show in my direct substitution at the beginning, but just to talk through that, 3 minus 3 is 0. 3 squared is 9. Minus 9 would give me 0. So 0 over 0. So then I said, okay, well, what can be factored? The denominator can be factored. So I said the limit of this function is equal to the limit of the same function in factored form. And then I saw my common factor, so I said the limit of the factored form of this function is equal to the limit as x approaches 3 of the reduced form of this function. When the x minus 3 and the x minus 3 cancel, make sure there's a 1 in your numerator. And then I retried plug in, so taking my 3, the x value that I was approaching, plugging it in for x, and I got 1 over 6. Okay, the last thing that we'll talk about in this video is actually a review for Math 3. And this is about finding, but using limit notation now when we approach infinity. X approaching infinity is also sometimes called in behavior. And so just a kind of quick recap, you really want to know your in behavior. Most functions, they are the same as their parent functions. They may just be reflected. So as long as you know your parent function's in behavior, that's good for the most part. Rational functions are a little tricky. If it's a rational function, meaning there's some kind of fraction, then you have to compare the degree of the numerator and the degree of the denominator. If the degree of the numerator is bigger on bottom, that means there's a horizontal asymptote at y equals 0, so the limit is going to be a value of 0. If it's bigger on top, there's no limit, so the limit does not exist. And if the degrees are the same, then you divide your leading coefficients to find the horizontal asymptote, which is also the same value as the limit. Let's take a look at some examples. We'll first do one where it's a known in behavior, and then we'll look at some of these special cases. So here I am finding the in behavior limit of this quadratic function 5x squared plus 4, and I'm approaching infinity and negative infinity. So it's really important to understand, well, what is the parent function and what has happened to that parent function? For all quadratics, I start with an up-shape u. Now this function has been vertically stretched and shifted up 4 units. But that doesn't really change the end behavior. It still says as x approaches infinity, on the right side of this graph, the graph is going up to positive infinity y values. So as x is approaching infinity on this quadratic function, we're still approaching infinity. So I'm going to say infinity, or because it's an infinite limit, you can say does not exist. On the other side, as x is approaching negative infinity, the graph of this function is going up to a positive infinity y value. So as x is approaching negative infinity, we are approaching infinity, which again can also sometimes be called a does not exist. So again, it's really important to understand your functions, their end behavior, and as x is approaching the ends of the function, knowing that end behavior. Okay, for rational functions, it's all about comparing, for the end behavior, it's all about the horizontal asymptote. So all three of these limits are as x is approaching infinity, and we're talking about on rational functions, notice they're all fractions. Whenever we're dealing with rational functions, we want to take a look at the highest exponent in standard form. So I have 5x squared plus 4. My highest exponent is the term with the largest exponent. So this is my highest exponent, and it has a degree of 2. On the denominator, my largest term with the exponent is x to the 4th. This has a degree of 4. Just a quick reminder, degree is talking about the exponent on the largest exponent when it's in standard form. So this is a case where it is bigger on the bottom. And anytime this is true, the limit is always 0. There's a horizontal asymptote in this graph, which is forcing this function to be 0. I'll show you the graphs of each one of these as we find the limit. So as x approaches infinity, meaning it gets larger and larger and larger, the y values are approaching the y value 0. So as x approaches infinity, y approaches 0. Let's take a look at the next function. I have a cubic function on top, so my degree is 3. I have x all by itself, meaning this is linear, and it has an exponent of 1, so this is a degree of 1. And when this is bigger on top, then there is no limit. So my limit here does not exist. Just to show you this graph, as x is approaching infinity here, you can see that this graph is increasing. So as x gets larger, the y values are going to infinity, meaning there is no limit. So when it's bigger on top, there is no limit. And the last case is when the degrees are the same. So here in my last example, I have x squared plus 4 over x squared. When the exponents are the same, meaning the degrees match, to find your limit, all you have to do is divide your leading coefficients, meaning you divide the numbers in front of those two terms. So 5 divided by 1 gives me a limit of 5. I'll show you this graph as well. So here as I trace this function, as x increases to infinity, the y values are forced along this horizontal value, this horizontal asymptote, so the y values are approaching 5. So again, just a quick summary of your 3 options. If the degree is bigger on the bottom, the limit is always 0. If the degree is bigger on top, then there is no limit. And if the degrees are the same, you just divide the coefficients or the leading terms, and that will give you your limit value. So 3 different cases of what to do. Bigger on bottom, bigger on top, and when they're the same. Okay, this last example is an example of ones that can be tricky. Whenever you're needing to find the degree and the polynomial or the rational function is in factored form, you are going to have to multiply out the function. So here I'm finding the limit as x approaches infinity on the rational function with 3x squared times 3x minus 8 in the numerator and 9x minus 1 times 3 plus 7x cubed in the denominator. I'm going to first fully multiply out my function because I need it to be in standard form. Okay, once it's multiplied out, you really don't have to do much more. And honestly, the more you do of these, the better you'll get. Because you're really trying to just identify the term with the largest exponent. So here in my numerator, my 9x cubed is giving me a degree of 3 in the numerator. And my denominator is this 72x to the fourth is my degree in the denominator. When the degree in the denominator is bigger than the degree in the top, and again, the degree is talking about the exponent. So this is a third degree over a fourth degree. And anytime it's bigger, the degree is bigger in the bottom, the limit is always 0. So again, sometimes you might have to multiply out a factored form in order to be able to find your limit. That's it for this video, and we'll do more practice with this in class tomorrow.